So thanks everyone. So my work is as a theoretician studying the evolution of Earth's atmosphere and the atmospheres of vaguely Earth-like planets. That is, I have no intuition at all for Jupiter-y-like things. And what my job, I think, as a theoretician is to change the way that you think about things. So in this 15-minute introduction talk to what I do, I'm going to just talk to you a little bit about Earth's atmosphere and some of the ways in which I think about it, with the hope that that will challenge at least some of you. So I'm going to look at the time as well to know how long I've got to talk. Okay, this is the atmosphere of Earth today. And I would like to classify the gases in three ways. There are noble gases, which we will not speak of anymore here, other than when we use them to tell us about things. They're so boring that they can tell us interesting things by what they do, but they just kind of hang out as gases. The other kind of gas, it turns out the one that behaves according to physics, that is water, is unusual on Earth. It's condensable. We have an ocean. It covers 70% of the planet. Water evaporates into the air, and that sets the amount of water that is in the atmosphere. That is simple. It is physics. There are some non-intuitive behaviors in that physics, but it is simple physics. Every other gas, I will argue, in Earth's atmosphere is controlled by a mix of geology and biology. And that's important because as we go to think about other atmospheres which might be Earth-like, we could think of a simple scaling relationship to say, well, if we've got a bigger planet, how much nitrogen or how much oxygen would there be in that planet? And that would be wrong. It would be bogus. You would have misled yourself. So we'll have none of that. It's all about the geology and the biology of a planet like Earth. So let's go on. These are some things that were seen earlier. We must remember that planets that have atmospheres are those that have not lost them, as shown on the Zarnley diagram. It's gone. We must also remember that any primary atmosphere that Earth had has been lost. So we can forget about solar composition. It's gone. And that is shown by these noble gas depletions. The atmosphere that we have on Earth is, some of it is outgassed. That would be the traditional view of an Earth-like atmosphere. But as I'll go on to show you later, a lot of the things that have gone into the atmosphere have then actually been taken back into the solid Earth. We have cycling from the solid Earth into the atmosphere, back into the solid Earth. And that is the paradigm of an Earth-like atmosphere. We typically think of the habitable zone as being synonymous with liquid water. So we then need to think about the properties of water. So I'll talk about a little bit about this unusual gas of water first. We want to be in this region to be habitable. The complication number one, and Dorian talked about this substantially, is that liquid water and solid water, ice, have different albedos. So we get a couple of different stable, steady states. We have a stable state which is entirely ocean. We have the stable state that we're in now with small ice caps. And then we have the stable state which is essentially globally ice covered. We'll talk a little bit about this one. We've got ice caps on Antarctica and Greenland. They're either there or not there. So, in the order of 30 million years ago with Antarctic glaciation, we went from here to here. And we can add small ice caps. In a few hundred years we'll have melted Greenland. It'll just go away. The last glacial maximum was adding in rather the Laurentian and Fennoscandinavian ice sheets. Those ice sheets just turn on and off. Like so many things in the Earth system, we don't vary smoothly. We vary from on, off. Ice sheets, on, off. Atmospheric oxygen, on, off. We have these transitions from different stable states in the way that Dorian was talking about. That field one would describe as really dynamical paleoclimatology, introducing dynamical systems theory. So that's the complication of water number one. This is Earth history. I said I'd talk about Earth's history. Shown here are glacials. We're in a glacial period now. Most of Earth was not glacial. It turns out that glaciation was fairly common, though, in the last 500 or 600 million years. The light blues are regional glaciations, polar. The white are these snowball Earth events, which Dorian derived a simple example of. There's a funny thing about Earth, which is glaciation is more common later in Earth's history when the sun is brighter. That is not understood. The implication is we have to have had this much stronger greenhouse effect early in Earth's history, and not only was it's stronger, but it seems to be somewhat more robust against regional glaciation. There's a problem in preservation. There's an exponential decrease in the rock record with age, but still I'm assured by the people who know the glacial record as well as you can know it, back to 3 or 3.5, the figure from Paul Hoffman, who is the biggest glacier nerd in the universe. Here shows me that there's actually not lack of preservation, but actually there doesn't look like there's much glaciation back then. That's curious. Very curious. I don't understand it. The other complication of water, and this is the runaway greenhouse, which has been talked about a few times, is shown here is the altitude of optical depth of unity. So as you turn the temperature up from the bottom towards the top of the page, the altitude of optical depth of unity rises up into the atmosphere. And it turns out it has a constant temperature. So if you look at the spectrum, and this is just in the infrared, the UV from Earth, it doesn't change. So once you get a moist atmosphere, this is what Kevin was talking about for the tropics today, you've got a limit on how much energy you can radiate. So water is our only gas that's controlled physically, but it's got these weird properties, ice versus liquid and albedo, and then this runaway greenhouse here, which make it water planets a little weird, or any planet which has got a lot of condensate that can evaporate makes it quite weird, and you get these really strong nonlinearities in climate states. So that's water. That's to make you feel safe and secure, in that these things behave in a normal way, or in fact a totally counterintuitive way. So let's do, one more water thing. If you just have water, no nitrogen, no oxygen, no CO2, no nothing, then your habitable zone is actually very narrow. And the classic habitable zone we think of is this darker blue area here. And it depends on planet mass, because the runaway greenhouse threshold depends on planet mass. Some other things depend on planet mass. You can also have this kind of strange pathological case in the light blue where you evaporate more water, so you get more Rayleigh scattering. So as you get hotter, you get a cooling, and you can have water on your planet, liquid water, while your surface temperature is, 400 Kelvin. So don't ever let anyone con you that liquid water means habitable, because it'd be difficult for any of us to live on a 400 Kelvin surface. All our definitions of habitable have to be parochial about where we think life would actually live, because I can make you a 400 Kelvin surface temperature liquid water surface. The point is, of course, the habitable zone is very narrow without greenhouse gas or background gas. So if you want a wide habitable zone, the kind of thing that Jim Casting will sell you any day of the week, you need background gases, and those background gases are controlled by geology and biology. So let's talk about one of those gases, which is nitrogen. Nitrogen used to be regarded as an essentially noble gas, that it did nothing, and there was always 0.8 of a bar of nitrogen in Earth's atmosphere. We now know that to be wrong. This is roughly where the nitrogen is at the moment. There's more nitrogen in the mantle than there is in the Earth, there is, if we put a part per million of nitrogen in the mantle, that's equal to 1 atmosphere's worth of nitrogen. And there's probably a few atmospheres worth of nitrogen in the mantle. There's probably a lot in the core. There's a little bit in the continents. The main point, the core is kind of inaccessible, but the mantle and continents, that we're going to exchange with the atmosphere through Earth history. And there's more than in the atmosphere. The question is, how did that evolution happen? Well, we know that it would have that nitrogen outgassed early because of noble gas systematics, or it outgassed at some point. The nitrogen in the mantle is not primordial. We know that the nitrogen in the mantle has gone with subduction. That is, nitrogen's been in the air. It has been fixed by biology. There is no other mechanism which is sufficient. It's been fixed to ammonium by biology. That ammonium has substituted for potassium in rocks because it has a similar ionic radii and the same charge, and it can then be subducted into the mantle. So we know that this cycle must have happened. There is no agreement whatsoever amongst those who would claim to be experts on this geological nitrogen cycle of what the history of atmospheric nitrogen is. If you want evidence of that, simply sit David and I down together and we'll argue about it. So that we talked about, and the history of nitrogen is entirely unknown. Again, scaling relationships will not work. Now, nitrogen's our background gas. We use it for Rayleigh scattering on Earth. So as a greenhouse gas, we mainly use carbon dioxide, and this comes down to life choices for your young planet. You can put your carbon dioxide in your atmosphere, and that would be Venus. If you took all the carbon dioxide, all the inorganic carbon that is stored in limestone rocks on Earth, and you baked that off in a lime kiln, as you would do to make concrete, to make this building, and put it in the atmosphere, then Earth would look almost exactly like Venus, apart from we still have to get rid of the water. Roughly the same carbon inventory. In Venus, it's in the atmosphere. In Earth, it's in the rock. This rock that you're looking at here, chalk, is made of bodies of dead organisms. That limestone is all biologically fixed calcium carbonate. So it's biology that's taken it out of the atmosphere and put it into the rocks. You can do it without biology, but it's a lot less efficient. So again, biological control. If you want to understand the amount of carbon in the atmosphere, you need to learn ocean carbonate chemistry. You can play with that. One of the handles is alkalinity. The handle, what you use to crank that alkalinity handle, is weathering of the continental rock. So that's geology, enhanced by biology. I'll move on. Oxygen, David talked about. The history of oxygen is well known because it does a lot of chemistry. There's all that redox chemistry that leaves us good geochemical markers. So David talked about that, so I will not speak of it more. And I will come on to my conclusions, thus I finish on time. And I would talk in terms of Vernadsky, who was a pioneering Russian geochemist but wrote in Russian and French, and therefore was not appreciated in the West until the last few decades when translations had propagated around. And Vernadsky saw the atmosphere as part of the biosphere. He saw he was the person who really defined the term biosphere. It had been introduced in the late 1800s, but Vernadsky defined it. And he said the biosphere has living and inert parts. We are living parts of the biosphere. The atmosphere is an inert part, but we cycle it through us. We breathe it in and out, both of ourselves and of the solid Earth. And the atmosphere, which is part of the biosphere, is the interface between the planet and the cosmos. It's what we can observe with our telescopes. So if we're thinking of Earth like planets, we've got a couple of things to think about. The first is that whether a planet is inhabited and habitable are inseparable, because the gases that are determining whether you could have the kind of temperature that life could live on are all controlled by life itself. The second thing is, oh, I'm out of time. We'll leave the second thing. Thank you. Sarah. Yep. Yeah. No. So the way that I view the great oxidation is, well, let's step back. So the origin of oxygen producing photosynthesis was probably about 3 billion years ago, and we see oxygen at percent levels in the atmosphere at 2.4. So I view the system like this: is after the origin of oxygenic photosynthesis and before the great oxidation, there was oxygen production and then organic matter degradation by methanogenesis. And then you had a flux of oxygen and methane into the atmosphere, and then they were destroyed photochemically. Then, once you get oxygen high enough, so that's about 10 parts per million, that you can produce an ozone layer. That ozone layer prevents UV photons getting into the troposphere where there's water, so it prevents them splitting water to make OH. And OH is really critical for the chemistry that oxides the methane. So once you go through that transition where you start to make an ozone layer, you slow down all the methane oxidation, and that allows oxygen to build up. So that's how you get this strong nonlinearity going to high oxygen from part per million to percent. The other thing it does is because oxygen's accumulated, then the biosphere can also oxidize a lot of the organic carbon with oxygen, rather than leaving it to the atmosphere to close that cycle. So, I would view the great oxidation as a transition from a low oxygen state where methane was oxidized in the atmosphere to a high oxygen, percent oxygen state where organic matter will be oxidized in the biosphere. No more questions. Wow. Okay.
Thank Colin.
They just kind of hang out as gases. The other kind of gas, it turns out the one that behaves according to physics, that is water, is unusual on Earth. It's condensable. We have an ocean. It covers 70% of the planet. Water evaporates into the air, and that sets the amount of water that is in the atmosphere. That is simple. It is physics. There are some non-intuitive behaviors in that physics, but it is simple physics. It's all about the geology and the biology of a planet like Earth. So let's go on. These are some things that were seen earlier. We must remember that planets that have atmospheres are those that have not lost them, as shown on the Zarnley diagram. It's gone. We must also remember that any primary atmosphere that Earth had has been lost. So we can forget about solar composition. It's gone. And that is shown by these, with the hope that that will challenge at least some of you. So I'm going to look at the time as well to know how long I've got to talk. Okay, this is the atmosphere of Earth today. And I would like to classify the gases in 3 ways. There are noble gases, which we will not speak of anymore here, other than when we use them to tell us about things. They're so boring that they can tell us interesting things by what they do, but every other gas, I will argue, in Earth's atmosphere is controlled by a mix of geology and biology. And that's important because as we go to think about other atmospheres which might be Earth-like, we could think of a simple scaling relationship to say, well, if we've got a bigger planet, how much nitrogen or how much oxygen would there be in that planet? And that would be wrong. It would be bogus. You would have misled yourself. So we'll have none of that. So thanks, everyone. So my work is as a theoretician studying the evolution of Earth's atmosphere and the atmospheres of vaguely Earth-like planets. That is, I have no intuition at all for Jupiter-y-like things. And what my job, I think, as a theoretician is to change the way that you think about things. So in this 15-minute introduction talk to what I do, I'm going to just talk to you a little bit about Earth's atmosphere and some of the ways in which I think about it